I'm Tom Charnock. I am a researcher here at the IAP. I'm a statistician and cosmologist and work mostly on machine learning. I come from Manchester and I did my undergraduate studies and my postgraduate studies at Nottingham and arrived here at the IAP about 2 years ago. Here I work mostly on developing statistical techniques and understanding neural networks and machine learning and how they can be applied to astronomy and cosmology. I work on large-scale structure mostly, and so this is trying to understand how we understand the universe as a whole and how we can model the universe and understand the parameters that control those models. I use machine learning to understand as a part of these models. So this means that when there's parts of the models that we don't understand or don't necessarily need to know about, we might be able to skip that part of the physics by building neural networks or other machine learning algorithms which allow us to interpret that data much more effectively. At the moment, machine learning can be used in science, but it's generally not used very well. The problem is that the results which you get from neural networks are generally just some output of an algorithm where you probably don't understand what that algorithm is doing. So in science, what we need to know is how much can we trust what the algorithm is doing, or how much can we trust that result. Essentially, that means that we really need to understand what this function is doing in a statistical fashion. So we don't do machine learning in the same way as Facebook or Google or these other big companies. Essentially, when they do machine learning, then they're learning to generate a face or to interpret voice. But it doesn't really matter if they get something wrong. Essentially, they have so much data that if they get one little bit wrong, it'll just look like a slight error. In science, we don't have that kind of freedom. We really want to be able to understand how much we can trust a neural network. Without that trust, then we can't interpret that as a scientific result. Currently, I am working on a way of being able to understand large-scale cosmology using large-scale structures. This is a very difficult problem in general because we as cosmologists like to use easy to calculate things. So one example of this is dark matter. So dark matter is something that we need to describe the way that structure forms in the universe. However, it's not something that we can see visibly. It's a computational tool, let's say. The galaxies that we see trace the dark matter we see in the universe. And what the link between the dark matter and the galaxies is some very complex astrophysics. We don't actually need to know that much of this complex astrophysics to be able to infer the cosmological parameters. So what we can do is build a neural network using physical properties which should mimic this tracing of the dark matter in galaxies. And by doing so and inferring the uncertainties on that neural network, on this physical engine, then we can be able to learn about cosmology directly from large-scale structure. So what we have here is the dark matter halo catalogue. So this is where clumps of dark matter clump together and within which you expect to find galaxies. We start with some initial conditions of the dark matter density, and we evolve those forward to some approximate distribution today. Then what we do is we want to match those conditions of the dark matter to the real universe, so the observations of large-scale structure and galaxy clusters. Because we don't know the exact map between the dark matter and the galaxy distributions, we're going to map the final dark matter distribution to the observed structures that we see in the universe. However, we don't exactly know what the physics is at that point. So we're going to use a neural network which we've built specifically for this purpose to infer the map between the final dark matter and the observed structures today. So essentially what we can do is we can learn exactly what the distribution of the initial dark matter is, as well as our neural network parameters. And by sampling over the parameters in both of the models, we're able to match much more closely to the observed data than we would be able to without the neural network. When I am building a neural network, I tend to build a physical engine. So by this I mean that we build in the physics that we're interested into the architecture of the network. And this makes a very eco-friendly network, which I always advocate. Unlike with Google or Amazon, where if you are trying to train a neural network to detect faces, then we don't have a model for what faces mean. However, in physics, we have physics to describe the processes that we are interested in. For example, if we have some astronomical data which is both translationally and rotationally invariant and is causally connected in some finite region, then we can build a network which incorporates those symmetries. Doing this, we can use far less data. We can train for much shorter times than the giant networks which are often needed by the large corporations. So one of the problems with the current use of neural networks is that you grab a giant neural network and you train it for days or weeks. And this is extremely computationally expensive, and it's extremely bad for the environment. So one of the things that we do by trying to build these physical engines is really cut down on our computational time and computational effort, and therefore build these eco-friendly neural networks. I am sure that machine learning and deep learning will be necessary for the future of astronomy and cosmology. In the longer term future, using Bayesian neural networks and building statistical frameworks which incorporates these kind of free functions that we're currently training using data, we're going to be able to interpret the science in a much more robust way than is currently possible. The dream situation would be to be able to really be able to pull all the information out from our data, to be able to constrain the models of the universe that we've got, so be able to interpret how the dark matter is distributed throughout the universe and what link that has with the galaxies, and from that be able to really understand our cosmological model and how the universe we see today has got to how it's got. As normal for a postdoctoral researcher, I don't exactly know what my next steps are, but I've always done what I've really enjoyed, and currently I'm really enjoying doing this research into understanding and furthering the statistical nature of machine learning. So I hope whatever I can do in the future still involves that work. I think I'm going to start.